Hello everybody and welcome. My name is Koen van Leeuwen. I'm from TNO the Netherlands, and in the following video I will be demonstrating a toolchain for architecture optimization of self-adaptive network signal processing systems. What we see here is the interface of the toolchain. We have implemented a domain-specific modeling language in the MetaEdit modeling tool, by which the user can model his system graphically using 5 different aspects. Here we have an example of which the physical model looks as following. The physical model is the first aspect, and it defines the hardware environment in which the system is running. Here we see that there are 4 sensor nodes, and each sensor node is communicating via the Zigbee wireless communication channel. If we look at the node definition of the node, which is the second aspect, we can see the technical specifications of the nodes. Now here we can see that we have one processor with a limited amount of integer operations, and depending on the operational mode of the processor, it will have a different power need. The same holds for the communication interface. Whether it's idle, receiving or transmitting, it will have a different power consumption and it will have a limited communication bandwidth. Also, the node has limited memory and it has a small battery as the power source. Now on these nodes there will be tasks running. These tasks are defined in the third aspect, which is the functional model. Here we can see the functional model of the demonstration example. In this example we have 4 sampling tasks, 1 for each node. The sampling task will communicate to the processing tasks, of which in this example we only have 1. Therefore we will have a centralized approach. However, if there are multiple processing tasks, we have defined here that the processing tasks communicate with each other in order to further process the information obtained from the sampling tasks. Now the fourth aspect of the model is the behavioral model, which defines the temporal behavior of the tasks. Now in this case, the sampling task, its behavior is very simple. Every 10 seconds it will do a sample, it will add some location information to it, and it will send it to the processing tasks. The processing tasks have a bit more complicated behavior, as it will have to gather information from the local sensor, information from the other processing tasks, and communicate the new information to the other processing tasks. In order to bind together the functional model and the physical model, the user also has to define the mapping model, which determines which tasks are running in which nodes. In this example, because there's only one type of node, all the tasks are mapped to the same node. Because there are multiple instances of the sampling tasks and multiple instances of the sensor nodes, we have to define this condition to determine which instance is bound to which node. When the user is done modeling his system, he can choose to export it to an XML file. Now this XML file contains exactly the same information as the graphical model, but without any of the visual properties. Let's choose to save it somewhere so that we can access it from our MATLAB session. We use MATLAB to convert the XML file to runnable MATLAB code, which is compatible with our Dyna simulation tool. So if we start the code generation tool with the XML we just created, and let's put the code in this folder over here. And we quickly see the generated files. This is the generated code of the node. Recall the battery and the memory that we defined in the graphical model, and the processor and the communication interface. Also, we have our state estimation task. And the other tasks that we need, as well as the setup scripts that will create the physical model and the functional model, and in this case, the mapping model. In order to start the optimization framework, the user has to provide a design space description file. This file contains the parameters which the optimizer can change. And in this example, the first parameter is the communication period between processing tasks. Generally, the higher the communication period, the lower the power consumption, but the higher the state estimation uncertainty. The next parameter is the processing task cardinality, which defines how many processing tasks there are in the system. The same holds here. More processing tasks means a higher power consumption and a lower state estimation uncertainty. The third parameter defines what sampling tasks communicate with what processing tasks. We can have a system in which every sampling task communicates to only one processing task. We can have a system in which every sampling task communicates to every processing task. Or we can have a system in which two sampling tasks communicate with one processing task. The fourth parameter is a bit similar, but it defines what processing tasks are mapped to what nodes. We can have a system in which there is one task assigned to each node. We can have a system in which every task is assigned to the same node. And we can have a system in which two tasks are defined for each node. Now the next thing is to get information from the simulation. And in order for the optimization framework to do that, the user will have to provide the loggers. Now in this case, there's one logger which will get the performance of the state estimation task. Another logger will get the power consumption from the nodes. Let's define here that we want to use the model that we just generated. And in the objective function, we have to define how to calculate the objective value from the loggers. Now in this case, we get the total power consumed from the power loggers, and we get the uncertainty from the performance logger. For this example, the objective value is a weighted average of the uncertainty and the total power used. With all these scripts in place, we can now start the optimization process. As the results come in, we will see this graph which depicts the energy consumed and the uncertainty of the state estimation task for each iteration in the optimization framework. Now note that we use a grid point optimization strategy, so it will try every combination in the system as the design space exploration file defines. This will take a little while, so for the rest of the demonstration I will speed up the video. When the optimization framework is done, we can have a look at the parameters that were found to be optimal. We see that for the first parameter, the communication period, an optimal value is found for 20 seconds. Apparently this is a nice balance between frequently communicating, but not too frequently so that the power consumption is relatively low, but the state estimation is good enough. The second parameter is the number of processing tasks, which is found to be optimal for 2, which is related with the third parameter, which says what sampling tasks are communicated to what processing tasks. In this case, we find that it is optimal to map 2 sampling tasks to 1 processing task. Because there are 2 processing tasks, this makes sure that each sampling task is mapped to a processing task. The fourth parameter, which is the mapping of processing tasks to nodes. And here we see that we should actually map 1 task to every node, because there are just 2 processing tasks. This means the first one is mapped on node 1 and the second one is mapped to node 2. This is the end of this demonstration. I thank you very much for your attention.